Okay, as we were saying, so on Friday we discussed this sort of field theoretic approach to the edge states and the relation with the bulk states using Chern-Simons theory as a way of understanding that and relating that to the work with the wave functions and the more microscopic approach with composite fermions that was greatly presented by our courageous chairperson. Okay, when you told me secrets, okay, my secrets, I have to say something. Okay. So we learned that, you know, there is a finite number of what we call anion types in a Laughlin state. So for a Laughlin state of filling fraction 1/m, there are m types of anion. So they are characterized in a sense by an anion charge. You may call it a topological charge. But in a sense, there is a fundamental one, which is the one with the lowest charge. Is the one, is the quasi-Hall that we saw in the form of the wave function. The higher ones, in a sense, can be obtained by a process called fusion, where you essentially take two fundamental ones and they approach each other, and then from some distance, they look as if they have twice the topological charge, and so on and so forth. But there is a maximum to this, which is determined by the value of m. So as I told you, the edge theory is done by, is a chiral conformal field theory. It's a very simple one. It's called the compactified boson. And it's said to be a rational conformal field theory precisely because it has a finite number of so-called primary fields that correspond to these different anion types. Okay? So this is an example of what people normally call an anion model. And it's the simplest one. Well, it's not, there is one that is even simpler, but I'll come to that later. Okay. Actually, I will tell you later today the relation between this type of ideas and the so-called ICTS-TIFR model, otherwise known or previously known as the deconfined phase of the Z2 gauge theory. At least when I was a student, that's the phase that I discovered. So at least it's the meaning of the phase was known before, but the meaning of that is one of the things I did when I was a student. So it's all work. Just go by that. Okay, it's fine. I have free time. Okay, no problem. Okay. Well, that's too small, by the way, for people in the back. It's okay? All right. Okay, so there is one piece. So this is an example of a state that we say has topological order, okay? Or quantum topological order. There are various adjectives that are being assigned to this. It's not a precisely defined term. For instance, if you have a magnet, you know what kind of order it has because it has an order parameter called the magnetization. There isn't an analog of this here. There is no symmetry breaking here. The time reversal symmetry is explicitly broken by the magnetic field. There's nothing spontaneous about it, okay? But this type of structure has been called a state with topological order or quantum topological order, depending the person who's giving the talk. Okay. Now there is an additional ingredient which is closely related to the existence of a finite number of anion types, which is a so-called ground state degeneracy. Or the particle physicists in the audience, if there is any, the vacuum degeneracy. On closed manifolds or surfaces. I will discuss a simple case of the system that instead of being on a disk, as we consider until now, we're going to consider a system actually that is actually defined on the surface of this torus. Okay? And actually, Ganpathy also discussed this briefly. this is not seen from here. Oh, good, I have blue. So a torus, this is called a torus, or a two torus, sometimes denoted by P2. Okay. And a torus has what they are called cycles. In other words, there are directions or loops that you can, so there are different types of loops you can define. On a torus, for instance, I can define a loop like this. But that loop can be contracted to nothing. It's topologically trivial. But there are two types of loops that cannot be contracted precisely because they wrap around the torus. Okay, so here is one. Let me actually draw it this way. Back. And the other one will be in yellow. I like these two colors because my favorite football team in Argentina called Boca Juniors. These are the, I know that. That's a footnote. We also won 7-1 against somebody else, as you know. Okay. Sorry, when I say football, sometimes in some countries it's called soccer, but it's football because you played with your feet. Okay. And here is another non-contractible loop. Okay, so there are two non-contractible loops on a torus. So imagine that you begin to look at more complicated surfaces, such as a pretzel. So you get it, more complicated things. Of course, this is all in fantasy land, in theory land. There is no theoretical, no experiment that can be done in a sample like this. Even if we could, it will be a little problematic to actually establish a uniform magnetic field, because, for example, here, in order to have a uniform field pointing out, I will need inside the torus, essentially a loop of magnetic monopoles. Okay, and it's kind of hard to come by one of them, except at Stanford in 1982, and it appeared and disappeared. It was good enough for a PRL, by the way, but it was only one data point and could never be reproduced, even by the author. So not everything that you read in major journals should be believed. That's an example of that. Okay, here actually, so you're going to see that in fact the structure is actually is rather elaborate. And there is a close relationship, in particular in the case of the torus, and then you can see how it extends to the others, with precisely the existence of a finite number of anion types. Okay, so it's a one-to-one correspondence, in other words, between the types, the degeneracy on a closed manifold, as we're going to call it, and the number of anion types. Of course, in this particular case, the anion types are all very similar to each other. We're going to see in the non-abelian case they are not. Okay, it's a little more elaborate than that. But let's look at this case. So how we're going, sorry. I'm going to give you a simple mathematical argument that I find appealing and elegant because it uses essentially elementary quantum mechanics to count the states on a torus. Okay, so let me remind you the Chern-Simons Lagrangian. So it looks something like m over 4 pi using the notation that Ganpathy introduced. It looks like this. And then I showed you that this actually meant two things, that A is A1 and A2 along the equal time commutator. So these are now their operators acting on the Hilbert space. This is I and a factor of 2 pi over m and a delta function between x and y. These are the equal time commutation relations, and that means that the two components of this vector field play the role of the canonical pairs. You can choose one to be the coordinate and the other one to be the momentum, the canonical momentum, not the linear momentum. They are different things. Okay? So this is one condition. And the other condition is that f mu nu, which we normally write like this, right? mu, F mu nu, in the absence of sources, if I don't have any currents, that F mu nu, you know, when I look at the blackboard, I speak more softly and also write smaller. That F mu nu, in the absence, if I had a current, then there will be a non-vanishing right-hand side, because essentially there is a Gauss law that we discussed last time that tells me that wherever I have a charge, in other words, there is a density, there is a flux. A flux means a local value of F mu nu, okay? But in the absence of that, notice that I have nothing here. The P is purely topological now. This is 0. Okay, then you remember that in kindergarten, they told you that if F mu nu is 0, in other words, if there is no flux, it's equivalent to what we call a gauge transformation. Okay? So you are going to say, therefore, that F mu nu, or rather the vector potential, A mu, will be d mu of some function phi. And this is actually how we discussed the connection with the edge before. Okay, but these are the small, so-called small gauge transformations. We're going to be interested when you work on a closed surface like this, on gauge transformations that wrap around these different cycles of the torus, the large ones. Okay? So in particular, there are two Wilson loops that I can define, just to give you an example. Let me call this curve here, let me call that gamma 1. Let me use this lowercase. And this other curve here, gamma 2. They are oriented curves, okay, but they are essentially correspond to these non-contracting cycles. Yes?
For the gauge field, little a, you require that little f is 0.
Yes, that's equation of motion.
Yeah. However, for the real physical capital A,
you mean
it will not be 0 because there is a real magnetic field.
Yeah, I'm working in Chern-Simons theory at the moment. I threw the honest to God vector potential to the dustbin of history. We'll come to that later, okay? For this argument, it's unnecessary. So if you want to know, if you want to probe the system, and you want to calculate what is the charge associated with each anion, what is the value of the whole conductance, etc., including the fractional statistics, well, for that I don't need it. For that, you need the vector potential, you need the probe magnetic field. Okay?
I'm confused because last time,
yes,
you assumed minimal coupling between little a and capital A,
yes,
which essentially meant that what I understand about little a, I also understand about capital A.
No, it's not. I mean, okay, in this approach, in this hydrodynamic approach, capital A essentially is needed to establish the state. Essentially, this is the line of magnetic monopoles that gives you the uniform. Okay? So after all the dust is settled and all that is done, I end up with this effective theory. And I don't need to talk about that again, unless I want to talk about the probe, the response to an additional electromagnetic probe, a small change in the, instead of having a uniform magnetic field, you have some electromagnetic probe that will allow me to establish currents and therefore to calculate conductances and things like that. Okay? So I'm not going to have there are no probes here. I am already deep in the state. Okay? And the uniform field is already taken care of. Okay, so the point is that this is not the only thing that can happen. And there are, as we discussed, as actually Ganpathy introduced, there are things called Wilson loops, operators. And so I can have Wilson loops on these contractible loops. And they may be interesting if you have two anions and then you can look at how they are linked to each other and what kind of fractional statistics they have. But I want to look at the Wilson loops along the non-contractible cycles that I have here. So let me call one gamma 1, which will be, in this case, is just e to the I, the circulation along gamma 1 of that. And then you see, I only go along one direction. And then gamma 2 will be along the other direction. Okay? So I claim that the best I can do with this small, and these are gauge invariant. So I can't get rid of them. So there will be, in particular, I can choose the circulation, which will be the integral from 0 to L1. So another way to represent the torus is as a rectangle. Here will be 0, here will be L1, this is the direction x1, here will be x2. And then you wrap it around, you identify the endpoints. So the opposite edges are identified so that this rectangle, see, that's how you make a tube, right? You take a piece of paper, you wrap it around in one direction, and then you wrap it in the other direction, you have a nice donut. Okay, that's what we do. So I will take this guy, and let me call this A1 bar. I'm not going to put hats. These are operators, but I'm not put, hats or anything. So I'm going to drop all of these hats. So this is the circulation. Okay, I can't get rid of that. So in general, the vector potential will look like A1 bar plus this part, which is the so-called small gauge transformation, which will have no effect for what we want to do. And similarly, the integral to L2, dx2 of A2 bar, and these are gauge invariant quantities. But I told you that A1 and A2 do not commute. Therefore, A1 bar and A2 bar will not commute. So we were going to discover that there is a finite dimensional Hilbert space associated with this state, okay, which is going to be the ground state degeneracy. Okay, so in general, as I said, A1 will look like D1 phi plus A1 bar, and A2 will be D2 phi plus A2 bar. 1 and 2 are X and Y, by the way. Yeah, there is something like that, just to make it. Yeah, I need. Otherwise, I have to 1, right? You mean here? Yeah. Okay. Otherwise, it doesn't make sense. Thank you. Phi plus A2 bar or L2. Yeah, in fact, it's in my notes, but I don't read it. Okay. Okay, so if I now take the action, not the Lagrangian, the action associated with that, and I specialize for this type of configurations, it reduces to m over 4 pi, an integral over time only, because these are constant, these are now functions of time, right? X naught is what I call time. They're functions of time. The X naught of epsilon ij ai bar d naught j, and this is what tells me that they don't commute with each other. Okay, notice that by having integrated over space, I get rid of these factors of L1 and L2. Okay, so this is telling me that A1 bar, which depends, as a Heisenberg operator, depends on time only, not in space. Okay, and A2 bar satisfy a Heisenberg type algebra, which is the, okay, so this is like X and P being the commutator being IH bar. I have set H bar to 1 here, by the way. Otherwise, you have to put factor of H bar and so on. So I can choose a particular representation, like the angle of the coordinate representation, or the momentum representation. And here, in some sense, they look very much the same. So in a sense, this is like a phase space. And so you can choose, for instance, to work in the representation, which I will call A1. And then A2 is a derivative of this differential operator. A2 will be minus I 2 pi over M d by d A1 bar. And then you can check that these two guys satisfy this commutation relation. Okay. Now the Wilson loop itself, which I call W, let me call it W gamma 1, which is e to the I, the integral from 0 to 1 dx1 A1 bar, A1. So the trivial part, which is the derivative part, this part cancels because it's periodic. And sorry, there is an L1 here. This is just e to the I A1 bar because if it cancels the factor 1 over L. And similarly, W gamma 2 is e to the I integral dx2 A2, just e to the I. So you just have two operators like this. And you're going to see that they act relative to each other as a shift operator, as a ladder operator. Okay, so let me define, so I have that. You can check by doing simple algebra the W gamma 1 and W gamma 2 and W gamma 2 and W gamma 1, not the commutator, it's just that, is e to the minus I 2 pi over M. Okay, so the product, if you just reverse them, you get a phase factor that you can see is essentially the fractional statistics that is raising its ugly head. It's there. Now, I can define two other operators. Let me call them U1, which is e to the I. My notes, for some reason, I have K, but let me keep with them. A2 and U2 to the e to the I M with a minus sign, A1. This is closely related to the guiding center coordinates, by the way. In a sense, we're looking at what the guiding center coordinates do as they go around these two directions of the torus. That's basically what this is. And they satisfy a similar algebra. So U1 and U2 is U2 and U1 e to the I 2 pi over M. Okay, it's easy to actually, you don't know, do you know how to, maybe if people don't know how to do this calculation, we'll discuss it in the evening. It's a simple calculation. Okay, so you have to expand in powers, you compute the commutators, and then you exponentiate. That's how it's done. Okay. Now, on the other hand, you could see that because of the way U1 is defined, U1 shifts A1 bar and U2 shifts A2 bar each by 2 pi. Okay, these are shift operators. Okay, it's like a ladder operator, as you will see in a moment. Yes? Sorry? They don't commute. There's an M. You mean here? There's an M. Wait. They don't, okay, so that's the correct answer. Thank you. Sorry, I will correct my notes. Sorry, this is, the hand is faster than the brain, you know. I was doing this at night also. I used to be a morning person. I'm not sure what kind of person I am now. Okay, so notice that this essentially is shifting when they're shifting each other. Okay, so it's a simple argument. In fact, this is a way. It's also a similar argument you can do for counting just simply if you have an integer number of flux quanta to counting the number of states in the Landau level if you put them on a torus. It's exactly the same argument. Yes. There are many clocks in nature. This is before the clock. Yeah, of course. Yeah, sure. That's why you get parafermions in some cases and things like that. Yes, but here, this is the same algebra you use for as I said, counting the number of states in the Landau level in a torus. It's exactly the same argument. Okay. So let me take the operator in particular, W gamma 1, and act. Essentially, these are unitary transformations, here unitary operators. I can act on the right with U1 and on the left with U1 inverse. Now remember that U1 depends on A2, therefore it's not going to commute with. Okay, and so you can see that this becomes equal to W gamma 2. Okay, so this is true. Yes. No, there is a minus sign here. U1 is like W2 and U2 is like the adjoint of W. It's like the adjoint, the dagger, yes. Yeah. Yeah, this is similar to but that's the same thing you do when you write down the guiding centers. It's very similar to this. Okay, so let me assume that I have, you need a minus only for this. Otherwise, it will be trivial. There is a relative sign between them. Yes, U1 is W gamma 2 and U2 is the adjoint of W gamma 1. And you need that for this to work. Okay. So let me assume that I have some state in a Hilbert, in this. So these guys are operators acting on some abstract Hilbert space. Okay. And let me assume that W, say gamma 1, acts on that with eigenvalue 1. It's a unitary operator, so you know the unitary operators have eigenvalues which are a pure phase. Okay, so I can choose that. And now I will act as about the following state, which will be W gamma 2. I want to know what is the W gamma 1 quantum number of that. For that, I act with W gamma 1. And now I use my algebra, and you find that this is equal to e to the minus I 2 pi over m W gamma 2. So that's the eigenvalue. Okay. And now you see, okay, you say, fine, let me take W gamma 2 to some power p, p being an integer. I can make the same line of argument. This is e to the minus 2 pi over m times p, W gamma 2, p, 0. So up to a normalization, that's what this is. So notice that these eigenvalues are exactly as you wanted to say. They look like the hands of a clock with m hours, and they basically change angularly by 2 pi over m each time. So at some point, when p is equal to m, they become, you go back to the original state. So it's cyclic. So this means that I have the number of inequivalent states, in other words, linearly independent states, is m. So it's a very simple argument, as you can see. Okay? So this is exactly, again, this is the same story as I said. If you simply want to have a uniform magnetic field and you have a particle that is actually going around really on the torus, this actually counts the number of Landau states. It's the same story. But I used it now for this case. Yes.
Two questions. Possible to see at this point.
Yes.
Question number one. Is it possible to see at this point that the inequivalent states, the M inequivalent states, have different density profiles?
No, they are uniform.
Only in the thermodynamic limit, we know.
Of course, we're always working here in the thermodynamic limit.
So there is no relation
The system
at this
is
point to density.
no, there is no relation. These are just uniform. This is the key point of a topological fluid. These are fluids essentially that can sense the topology of the surface in which they live. Otherwise, they are completely uniform. So this degeneracy is not related to symmetry breaking. That's the whole point. So for instance, if you take a magnet, like an Ising magnet, okay, always goes back to the Ising mode, sorry, it has a two-fold degenerate ground state. But that degeneracy is the same if you work on a surface with 2 to the 18 handles, it will still be 2. It has nothing to do with that. It's an internal symmetry that is spontaneously broken. This is exactly the character of a topological fluid. It's because it can sense the topology of the surface. Okay. So for instance, let me continue, and then you do that again. If I go to my pretzel, then there will be more non-contractible loops. Okay, so this is an argument. This goes back to work by Shogun Wen and Chan Yu around 1990, I believe. And what they showed is that the degeneracy, which is to say the dimension of this Hilbert space, is 2 to the G minus 1, where G, no, it's 2 to the G, sorry, where G is the Euler number, if you wish, or the number of handles. Of the surface. Sorry, M to the G. It's M to the G. So it grows exponentially with the topology in particular. Okay, so in fact, they actually wanted to think, in fact, I think this was probably the first proposal of a qubit or a qubit, I guess it's called in this case, because essentially they wanted to think that if you put this on a torus, then you could manipulate the states. You have this finite dimensional Hilbert space that is totally oblivious to anything that is local. It's protected in that sense. Okay. Now, you may have wanted to see this at the level of a wave function, and this was done by Haldane and Rezai around 1990 or 91, I think. Shortly after that, which basically consists of taking the Laughlin wave function, which looks like this, as you know, times these exponential factors. This is correct for a disk, but not for a torus. For a torus, you have to replace every factor of z by a suitable theta function, which are quasi-periodic functions. And then by looking, oh, hi, how are you? Long time no see. By looking at the zeros of the theta function, they show that, for instance, for the state 1 over m, there are m inequivalent arrangements of the zeros of the theta function that correspond to m linearly independent states. Okay, and those states are just as uniform by the usual argument. And back to you.
Okay. So the second question,
Yes.
I'm trying to understand whether one can go or connect bosonization in 1D to this picture. And the picture I have in mind is you take this torus,
Yes.
and then you introduce a sort of ridge potential, which becomes larger and larger until the torus is disconnected into a cylinder. Yeah. So there is a dry area. I mean, there is incompressible liquid everywhere, and there is a dry area.
You want to actually cut the torus open into a long cylinder.
So yeah. I know that when I have this cut, this cylinder, I can talk about edges, and I have right. my bosonization in 1+1 dimension and so on, yes. And I can define the densities, for example, at the edge and so on. So, but at the same time, I can use the same Chern-Simon gauge field. So can you point out which fields, which combinations of these A's will lead eventually to this edge bosonic fields? Can you make this connection?
No, the problem is in that case, it's equivalent in some sense to work with an annular disk, the case that you are discussing. Okay, so if I want to cut my torus open, it's equivalent geometrically to work not on a disk, but to work on an annulus, an annular region with a. So let me draw it here. So we start with this, right? And then I can do the cut that you want. Then it looks like this. And now I have edges that circulate in opposite direction. They are counter-propagating. But this is equivalent to doing this. Okay? And so then you're back to Laughlin when you do this. So there is no degeneracy in this case, because there is, as you can see here in particular, and this is something I wanted to emphasize, this depends on the topology of the manifold. Okay, suppose, and actually there was a big fight in the 1980s between Duncan Haldane that liked to work on the sphere with a monopole in the middle, and people that wanted to do numerics, I think Yoshioka and others, that wanted to work on a cylinder, on a torus. And the people on the torus found that the 1/3 state had a threefold degeneracy, which originally was mistaken for a charge density wave, because in the thin torus limit, it looks like a charge density wave. There was a famous state by Tau and Thouless that actually looked like that. And then, but Haldane said that's wrong. They are getting the wrong physics. The state is unique. Well, they were both wrong and they were both right, because the answer depends on the topology of the manifold. Now, this situation is essentially the same as the disk. Okay. So instead of the topology, in a sense, is absent in this case. It's just a multiplicity of anyons. This is the relic of that on the edge states. So this tower, if you wish, or so-called primary fields of my edge theory is what is left after you do this cut, after you cut the torus.
I was not asking about the degeneracy. This is clear. I was asking about whether you can take those fields and identify which combination is my
There is
bosonic fields on the edge.
the bosonic fields on the edge are the field phi. Because you work on a manifold that is topologically trivial, so there are no contractible, you don't have any non-contractible loops in that case. Okay? Now you could define, and this is true, a Wilson arc, if you wish, that comes from here to there, okay, something like that. That you can do, or rather the other way around. Okay? So you can define such operators, and you can define also an operator that goes around like that. But at the level of the edge, you don't see it. You have to go through the bulk to make sense of this. So these A1 and A2, essentially, this becomes A2, which and something like this becomes A1. Okay, this is a little bit like a more complicated version of the Aharonov-Bohm effect, because these two guys don't commute now in this case. So that's the only thing that is left. So they will appear, for instance, in processes where you want, precisely if you want to do the Laughlin argument, where you want to transport some charge from the inner part of the annular region to the outer region. Okay, so those things do exist, and they will not commute with each other. And they satisfy this algebra. But there is no degeneracy in that case. Okay? Because the boundary condition now fixes it. More questions about this? Okay, so you may think, yeah. Well, it's just more of the same. You have more non-contractible circuits in that case.
Yeah, but you don't remember what's the algebra.
Maybe the Ortiz algebra. I don't know. I don't know the name of the algebra. This is a simple, essentially. I guess this is still the Heisenberg algebra secretly. Okay. It's not, okay. It may have whoever's name it does, but okay. But in a sense, it's secretly still the Heisenberg algebra. But with some in the Heisenberg algebra, there are no bounds. Here is bounded, okay, because of you work with these operators which are unitary directly. Okay, so this is essentially what the content of the degeneracy is. And what these guys did is to show at the level of the wave functions written essentially on the torus. Because you're in a torus, you have to work essentially, you can still work with complex coordinates as one defines the wave function, but they have to satisfy the quasi-periodicity condition. And so the natural expression is to work with the theta functions. And then they show that there are m inequivalent versions of this. There isn't a unique wave function anymore, in other words. So the Laughlin wave function, there are m versions of the Laughlin wave function, in other words. Okay? Okay, is this clear? Because I'm going to go to the multi-component case now.
Is there some kind of relation between the Wilson loops and quasi-particle operators?
Yes, they are. That's what we discussed at the last time. The quasi-particle operators essentially are so if you want to say from the point of view of their time evolutions, at least adiabatically or quasi-statically, are essentially the Wilson loops correspond to the word lines of the quasi-particle operator.
And that is this well defined even in the annulus, for example.
And be defined that it doesn't matter. What matters is that there's always the essential condition that these loops cannot cross each other.
Okay.
Otherwise, the notion of fractional statistics is meaningless. It doesn't exist.
Right. Okay.
There's no linking essentially in that case. All right. So what I'm going to do now is to do a bit of more of the same and talk about the so-called multi-component states. Okay, let me erase the blackboard. We're going to use the same ideas for studying them. You can use them with wave functions. I will show you the wave functions. They were proposed by Halperin in that case. Okay, so we'll erase as I need, okay? So preparing I want to discuss multi-component quantum Hall fluids. So imagine in that case could be, for instance, that the electron spin is not fully polarized. So you can imagine that can happen if you can tune the gyromagnetic factor to be small, to be zero, in fact. And that can be done in gallium arsenide, for instance, in the high density regime by applying hydrostatic pressure. You can, in fact, flip the sign of the gyromagnetic factor. It's so small that you can do that. So you can actually study phase transitions between states which are fully polarized, in other words, where the Weizmann energy plays an important role, to a state which will be unpolarized, where the Weizmann energy doesn't play a role. So in a sense, the multi-component state we'll discuss is an example of what is called a singlet state, because it doesn't, essentially is unpolarized. But you could also have, a more complicated heterostructure or system where you have many components, many fluids, many two-dimensional electron gases, say 2 or 3 of them, and people make these things in the laboratory. And then you can see how they interact with each other, and they give rise to novel types of fractional quantum Hall states. They are all abelian, okay, but they are new. Okay, preparing for that, I'm going to do multi-component transitions. So now I'm going to have not one hydrodynamic field, I'm going to have n of them. Going from 1. N is not the number of electrons now, it's the number of types, if you wish here, of fluids. Okay, and let me write a Lagrangian for this. I'm going to assume that there is only one electromagnetic field, which in some sense is obvious. However, in the actual sample, sometimes you can actually differentiate the electromagnetic field on one fluid from the electromagnetic field on the other fluid. So sometimes you can actually have a more elaborate version of this. Okay, so I'm going to write a simple extension of this. We still have a factor here. And instead of a single level, as we called it before, level M, we called it before, we're going to have a matrix, okay? So this is sometimes called the K matrix theory. There's nothing to do with K theory, by the way, that some people love. Okay, this is not that. This is something that was proposed by when Z. Okay, back around 1991, 92. Forgot. There is a beautiful review, by the way, by Wen that was already mentioned by Ganpathy, which I follow not closely, but similarly. This is in Advances of Physics, 1995. It's a really nice review. And it hasn't dated. Okay, the only problem is the PDF file is not searchable. But aside from that, it hasn't dated. Okay, so Kij, I'm going to have my usual epsilon tensor. I will get rid of it in a moment. Oh, I forgot to put my indices here. A mu, B, lambda, I. Okay. So I want to, again, remember that the curl of each one of them defines a current. That's what we discussed last time. So that's why, because if you have multiple fluids, there will be multiple current operators I can define. Or if you think in terms of spin, there will be a charge current and a spin current, and so on. So there will be a term which will still be E over 2 pi. The honest to God vector potential that our co-chair wanted. There it is. Something which we call a charge vector. So the charge vector is a vector in this internal space, in this indices times epsilon mu lambda a nu I d lambda. Sorry. Yes, the lambda. I don't want that. Epsilon d nu a lambda, and here will be I. And in principle, I'm going to have these quasi-particle currents, but there could be many of them. So I'm going to have NA mu I, and there's also something which we are going to call a quasi-particle vector. We call it Li. So notice that this is a vector whose number of components is the number of species, and these are all integers. Yes, these are the word lines. That's what they represent in this theory. Again, we send the gap to infinity. We don't get rid of all the local physics, if you wish, and we're going to look at only the topological. So I'm not going to go through, so this is a vector that is made of n integers, okay? And this is, I need to define this, it's up to me depending on how I think about this problem, okay? So both are going to enter. I'm going to give you some results. The derivation you can find in my book, or in your book perhaps too. It's in my book. It's in my book from 2013 in particular. So you can look at my book. I need to advertise my book, which is from 2013. Okay. It's supposedly a second edition of a book I published in '91, but it's 3 times as big. So it's not really in the second edition. Okay, so what is the vacuum degeneracy? You can generalize our argument that we made today, and it turns out that the degeneracy is the determinant of K, absolute value, raised to G, where G is the number of handles. So that knows about the topology. Okay, that's because I have several. Imagine if K was just simply a diagonal matrix, then I will have M1 to the G, M2 to the G, M3 to the G, etc. If you multiply all of that, it will be the determinant. Okay. But you can prove this using the line of argument that I use here. So what's the filling fraction? Let me call it nu, which is to say, what is the whole conductance of this? Is the inverse matrix of K, component Ij, Ti, Tj. So that depends exclusively on how my fluid coupled to the electromagnetic field. So it depends on it. You think of this is defining some kind of metric in some sense, because it's a bilinear form. Similarly, what is the charge? So the degeneracy, filling fraction, the charge, let me call it Q. Now Q will depend on your choice of L's, okay? Because it will depend on the quasi-particle, and there are different quasi-particles here. So it's going to be the charge is minus E. We have the units of electric charge, K to the -1, Ij, Ti, Lj. Okay, so I'm just not going to derive this. I tell you how to compute that. So in other words, you have this matrix K for a given case of the fluid. I'm going to discuss a couple of examples in a moment. They compute the inverse matrix. You do this with some choice of this so-called charge vector that will tell me how they couple to the electromagnetic field. That tells you the Hilling fraction. This is going to tell me the charge for one part. Each type of quasi-particle will have a charge, as you can see from here. And now you can look at the statistics. We call theta of L. Is pi times k inverse ij, and you guess it is Li and j. So this is what I will call the soft statistics. Okay, so this is the statistics of each type of quasi-particle. If you take two of them and you compute them in reverse order, this will tell you what the fractional statistics is. But there's also a mutual statistics. Now, because I can't do this adiabatic transport from one type of quasi-particle and the other, and they will not commute. Okay, they will get essentially get entangled with each other. And in that case, the depends, let me call them Li and Lj prime. There are two types. And this is pi k inverse ij, still Li Lj prime. So it tells me how they actually get linked together. Okay. Yes. Yes. Yes.
If you take one component.
Yes. Yes.
And you put the quasi-particle. The way I remember it.
Yeah, that's what we did last time. Yes. Right. I know. I understand that.
So now, if you have many components, I would say you have red quasi-particle, green quasi-particle.
Right.
So I should distinguish them as current operator. But now,
They do, because each current essentially has a label I. This is not the electromagnetic current. These are the word lines of the quasi-particle. That's why there is an L here. L, yes, right, we'll have this, right. And the way I manufacture that is by saying this is going to be some vector field which gives me the word line, and this is what attaches a particular character. Yes. Well, if you want, okay, you can define this if you wanted. You could have defined this to be. The problem is I can put a mu and a quasi-particle and an I. If you want. This begins to look like chemistry now, right?
Okay, but the way it looks now is like one day.
Well, okay, so the moral is that, okay, so what this is telling you is that that defines the word line. And this tells me what is the L associated with that word line. Fine. Okay, this is the way you give it, this is the way in this framework you give it an L, you give it a label. Okay. Sorry. Okay. Okay, so this, if you want, given this, you can basically figure out for any system of this type. I'll tell you in a moment what systems do these things. Sure.
The Chern-Simons computes for you is not invariant.
Yes,
the lines
correct.
are knotted, and then Weiss is with a phase. If we have a K matrix, is there?
It is essentially a not invariant. but in this tensor product space.
Right, but it's not must be multiplied by some expression in
This is essentially the not.
Okay, yeah.
This is the not invariant. That's what gives you the self-statistics.
Okay.
And this one essentially gives you the mutual statistics. Okay, before I actually discuss the actual multi-component states, I'm going to make a small detour to a relative of this theory that is called the BF theory in a very uninspired way, which turns out to be the theory, the topological field theory of all the toric codes and their relatives. You can see that all of them can be written in this fashion. So, for people that like to classify things, this is a way to do it. Okay, so let me tell you a little bit about what this BF theory is. In a sense, it's already written here in some sense. But as a response, we're going to have it somewhat different. So this is an BF interlude. You know, in the old days when you went to a movie theater and you had a 4 hours long movie, they usually have a break so you could go and have coffee, go to the bathroom and all of that. It was called the interlude or intermission. We'll do the same. So this is called the BF theory and the toric, so-called toric. Okay, so if you remember, I'm sure you remember everything I said in my so-called distinguished lecture. I'm not sure how distinguished I was. Okay, hopefully I was sufficiently distinguished. So sorry, I like to make these jokes that some people may not like, but they are mine, okay? So okay, it's not that I don't appreciate giving a distinguished lecture, but I don't know how distinguished was my actual lecture. Okay, so.
Distinguishable from other
Okay, so yes, so it's not, okay, let's not continue on this. Okay, so we talked about briefly about the so-called gauge theory in 3 or 2 + 1 dimensions, and we said that there is this deconfined phase that is equivalent to the toric, to Kitaev toric code. To me, when I was a student, this was just a deconfined phase, which had a peculiar property that I couldn't find any local operator that would create a charge. It was non-local. So I could have discovered in 1979 topological field theory, but I always wanted to work in the thermodynamic limit. I never cared about boundary conditions. Therefore, I missed it. Okay, so sometimes you have to be careful with that. So I could have discovered it, then I didn't. But you could see that there was an element of that, because you could not create a local charge in that theory anyway, any more that you can't here either. You need to have this kind of Wilson arc to do it. So it's similar to it. We can say, as Wilson said in his Nobel lecture, that one of these bad graduate students that keep solving their thesis over and over again in different fashion. Okay, so in the rhetorical is usually defined for Z2, easily extended to Zn. People have done that. It's a rather elementary thing to do. So I'm going to show you that the relative of this has the same content. It's not a lattice model, it's a continuous, it's a topological field theory. Okay, but it has exactly the same topological content of the so-called toric code. I'm going to write a Lagrangian that will look very much like Chern-Simons. It's a 2 pi, not a 4 pi. But it has 2 gauge fields, A and B. Okay. And since the curl of B, if you put the epsilon here, this looks like a curl of B, is called F. Then this looks like, well, sorry, if I put the curl in A, then B is coupled to the curl of A, thereby the name BF. It's a very uninspired thing. This theory, in a sense, is a theory of mutual statistics. Okay. And this was, I think, done first by the gravitational guy in Santa Barbara. Oh. No, no, Project, no. In the department. Oh, we'll come back later. Okay. Okay. Right, so I'm going to write this in the form of a K matrix for you. Okay, after all, it looks like that, okay? Except that I don't have, it is like a K matrix that will be off diagonal in this case. Okay, now will be n, 0. So the diagonal terms are 0, therefore they disappear from this expression. And you get these non-diagonal terms, which you want is n times sigma 1, if you want to use the terminal. Okay, is that thing? What is the degeneracy? Is the determinant, the absolute value of the determinant of k raised to the topology, essentially the number of handles. So here is n squared on the torus. Let me work on it. Okay. So for the toric code, n is 2. For the toric code, there are 4 anyons, as predicted by this. They are labeled by the identity. Something is called the E enyon, the M enyon, and E times M, which is effectively a Majorana fermion. So let me call it chi so people don't get confused. Okay, so this is Majorana. In fact, if you take the C2 gauge theory and you go through an analog of Jordan-Wigner, you find these things immediately. This is work that I did back in 1980 with Mark Stepnicki, many such things. These were my 6 months trying to solve the 3-dimensional Ising model was part of it. Okay, so in this case, you see that you get this. This is essentially for the same reason you have a Majorana in the 1-dimensional chain, you get it. Here is a little more elaborate because you have to go through the lattice construction. Okay, so there are, again, as I said, here I can define a Wilson loop. Let me call it on some loop gamma. E to the I, these are not arcs, they are loops, gamma. And let me define, this will be for, this will correspond to the E particle in this language. And let me define this, so the M particle will be on different loop. In the lattice construction, this guy is on the direct lattice, this guy is on the dual lattice. But in the continuum, you don't make that distinction. They're just 2 different loops. In the lattice construction, this is a Wilson loop, and this is called a Tuft or magnetic loop. So this gives you Wilson. This is called Tuft. Now they are linked. So if these loops intersect each other, they get some linking. So if linked, then they anti-commute in the case of Z2, N equals to, then they let me call it W gamma P and W gamma tilde M, they anti-commute, so they have mutually, they behave as they were fermions. And you can do the lattice construction. I do that in detail in my book. It was done by a large number of people. Essentially because they don't commute with each other, they anti-commute. In the case of Zn, then you have this kind of clock algebra. Okay? And on the other hand, the guy Chi is this Majorana fermion, which is the same. Okay, so this is actually what is called the BF theory. And if you actually work with a lattice model, you find that it has exactly the same number of anyons, the correct degeneracy. So this gives you the same theory. There is a relative of this on the double fermion model. So the semyon is essentially something that has statistics pi over 2. And so if you have a k, which is m and minus m, or 2 and minus 2. Notice it has the same degeneracy as that because the determinant is still 4. Okay. Each one of them will have self-statistics pi over 2, but they commute with each other, so they are mutual bosons in that case. Okay, so this is another possible model that you could define. You could think of this as a Laughlin state for bosons and another Laughlin state with a reverse magnetic field, and they are stuck to each other. Okay, because essentially time reversal is broken by this guy and by that guy, but in opposite ways, so they cancel. So time reversal is restored, time reversal in one, and the permutation of the two give you a symmetry. So even though the determinant is 4, they are very different topological orders. Okay, so the degeneracy doesn't really tell you everything. So you need to know the full structure. So in that sense, this type of topological order is very different from an order associated with an order parameter. I hate to call it the Landau order because it's just order. Okay. So it's very different in that sense because it's not characterized by a single operator, an order parameter. It's characterized by a structure. This structure is called topological order. There is a more elegant term in mathematics. It's modular tensor categories, but I will not talk about that.
I have a clarification question. I mean, on the lattice, you have C2 cross C2. So here in the continuum, you have only one C2.
No, in the lattice, you have just Z2. It's a Z2 gauge theory.
No, I'm talking about, I'm talking about the toric code. You have C2 cross C2.
You have Z2. That's all you have.
You have C2.
It's a Z2 gauge theory. That's wrong.
There are two sets of loops.
Yes, there are two sets of loops. There is a Wilson loop and there is a magnetic or 12th loop.
Yes.
Okay. Okay.
Eduardo, you have until 10:30 because you started 5.
Yes.
Give more time.
Okay, I want to actually tell you about the physical realization of this. Okay. So this is I wanted to give you a parenthesis on this because these things are, people think about them, and normally they think about them as if they were, in a sense, different beasts. The only difference is that these states do not break time reversal symmetry. Neither this state nor that state. They are topological fluids, so presumably you could get states of this type in some time of frustrated magnet. There are various proposals for that. They have yet to be realized experimentally. Because they are magnets, you can think of the spins as hardcore bosons. The common one represents them in that way. So it's natural to use this type of representation. Okay, so let me tell you about the realization of this in terms of actual quantum Hall fluids. Of course, this actually, what I'm going to say now predated what I just discussed. I wanted to give you the general structure, and now I will tell you how they show up in specific cases. Okay, so multi-component. They were first proposed by Halperin, actually. In 1985, I think, 84, something like that, very early, before any experiment, in fact. So these are I call them the M&M states. You know what M&Ms are? These type of sweets that at least they are sold in the US. I don't particularly like them, but I'm going to give you a particular version of this. These are integers. They are the generalization of the level of the Laughlin state. And okay, let me. I need a bigger blackboard. Okay, sorry. Okay, so I'm going to write down a generalization of the Laughlin wave function, which is what Halperin did. And the wave function for these states, there are other versions of this. Think of this as two different fluids, or up and down, whatever. And let's say that one type of fluid held coordinates z. They still go from 1 to n. There are n electrons in E to 10. There will be some other set of complex coordinates called W. And up to a normalization, this is the product for I less than j, zi minus 3j to the m, wi minus 3j to the m. Okay, so this looks like just a product of two Laughlin states times something for I and j from 1 to n. Notice that I don't need to have that. So, okay, so it's a z, sorry, I can do it less or equal. Okay, let me do it just here. N times this exponential. Usual exponential factors. Okay? You can work it out by going something like what Ganpathy did, looking at the state with higher angular momentum, the highest singular angular momentum state that is occupied. And you can find that the filling fraction is 2 over m plus n. By choosing these two indices to be the same, I am assuming that the two fluids, in a sense, are equivalent to each other. They have the same character, or in other words, that they have the same filling fraction. I could actually have an imbalanced state where these two fluids have different numbers of particles, and they have an M1 and M2. Okay? But let me keep it simple. Okay? So this is a filling fraction. Okay? It's a total filling fraction. Again, this has to be anti-symmetric for fermions, symmetric for bosons. Okay? So if n is m minus 1, one can prove, we'll see why in a moment, but one can prove, and you think of the two labels as up and down spins, that this actually leads to a condition that these are spin singlets. In other words, that they are unpolarized. But this is only true for this particular combination. Again, M has to be odd for fermions. Fermions. M even for bosons. And there's no restriction on N. N can be any integer. Okay, so what is the K matrix theory? You can read it off essentially. It's a 2 by 2 matrix now. So K will be 2 by 2 because there are two fluids, and it's just M, M, M. That's all there is to it. Okay. The charge vector, and this is if I assume that both fluids are coupled to the same electromagnetic field, then the charge vector is 1, 1, because both are coupled the same way. Okay. And the L's, okay, so in principle, there are different values. So Li, there are two, so this will be L1, L2. Depending on the value of M, there will be different numbers. So for example, I can take the fundamental Laughlin quasi-particle of one fluid. So here you see you're going to have, once this is has a non-diagonal part, so this is like the BF theory that I just told you. So this has both the separate Chern-Simons terms and the mutual term, which is like the BF theory I just discussed. So they are both together here. So you get both the self-statistics and the mutual statistics in this case. So the charge in this case, so let me take Li to be, say, 1, 0, or 0, 1. These are the fundamental ones. There are many more you can write. I will tell you for the fundamental quasi-particle. They have charge Q, which is plus minus E over M plus N, and statistics pi, which is pi times M over, sorry, yes, over M squared minus N squared. And notice that the vacuum degeneracy is going to be the determinant of this, which is M squared minus N squared absolute value on a torus. So it's to the first power. Otherwise, it's to the number of handles on the torus. P2. And again, you can write the analogs of this by replacing the z's and the w's by corresponding theta functions. And then everything works at the level of the wave function and the level of the effective field theory. Let me tell you the prominent states which are seen. And there is also a Jane version of this where you can essentially think of the Halperin states playing the role of the 1 over M states, and there are these Jane towers that sit on top of them. You can play the same game about this. And I did that with my student Lopez in the mid-90s. So examples. I'll tell you the important ones. It's a state called the 3-3-1, which is to say M is 3 and N is 1. This state has filling fraction 1/2, interestingly. Well, let me first say, well, the matrix, of course, is 3, 3, 1. The K matrix. The degeneracy, so let me have a new degeneracy. Charge and statistics. I'm going to have a little table for different states that I will discuss. The degeneracy on a torus is 8. The filling fraction is 1/2. Sorry, the degeneracy, yes, it's 8. The charge is plus minus E over 4. And the statistics is 3 pi over 8. So those are, and again, depending on the value of M, you have a tower of possible Ennion states, Ennion types that you can define. Okay, so this is one particular, let me write the K matrix here for you. In this case, it's 3, 3, 1. There's another state called 3, 3, 2. This is beginning to sound like numerology here. This has a matrix, of course, this. The filling fraction is 2/5. It's an interesting number, okay? Notice that 3, 3, 2 corresponds to the case where n is m minus 1. Okay, m is 3, n is 2. So this is a spin singlet state. Okay, but I'm going to come to this. The degeneracy, in this case, is 5, which is, by the way, the same degeneracy of the 2/5 state Jane, which is fully polarized. The charge is plus minus E over 5. And the statistics is 3 pi over 5. So what's the difference between this state and the Jane state at 2/5, which is fully polarized? Well, the difference of this state is unpolarized. So there are additional spin states, spin excitations you can define, but the topological order is the same. In fact, people have seen in this particular case, by adding hydrostatic pressure, there is a phase transition between, it's actually a very sharp first order phase transition, modulo effects of disorder, between the fully polarized state and at higher pressures, this unpolarized state. So this is that's this state. It's a close, this is the spin unpolarized relative of Jane. I'm coming to that. You read my mind or my notes. Okay, so let me call it state.
So I have a question about
1,
this
1, 2. Yes.
case. Okay, first question is, isn't there a charge 2e over 5 in this state?
No, it's E over 5.
Okay, but like, okay, okay, the next question is, what
So
is the,
think of Jane is always a denominator that enters. Okay, that's all there is to it. Well, it should be. There was some question with the noise experiments and all of that. Let me not get into that.
okay. And what is the essential difference between statistics of 3 pi over 5 and one which is from which you subtract pi or 2 pi? You have minus 2 pi over 5. It was detected in the.
Can we discuss this later, please? Okay, I can't understand you. We are close to the end. I'm sorry. Okay.
Okay.
Yes. Okay, so let me look at this state that you will get with 1, 2, 2, 1, 1, 2. This is K matrix. You can do the computation. The filling fraction is 2/3 indeed. Okay. And the degeneracy is 3. And the charge is plus minus E over 3. And the statistics is minus pi over 3. So this is singlet, and this is fully polarized. Okay, let me put it that way. So there is actually a Jane state with filling fraction 2/3, which is fully polarized. Is one of the so-called, playing the role of the Laughlin state in the reversed particle Hall sequence. Okay. And again, so this was done experimentally by applying hydrostatic pressure. They went from one state to the other through a phase transition. Okay, so these states exist. The only difference is that there are additional excitations that you can get here associated that you can classify using essentially the spin algebra, the SU2 algebra. Okay, so what is there's another way of writing the Chern-Simons theory, which is instructive. And with that, I want to end. because this state has an additional character. There are so-called neutral and charged edge states. So you can now go to define two new fields, A plus or minus mu, which is 1 over root 2, A1 plus or minus mu, A2 mu, symmetric and anti-symmetric, okay. Bonding and anti-bonding if you're a chemist. Okay. The Lagrangian now becomes m plus n over 4 pi, A plus d A plus. There is a coupling which is minus root 2e, A d A plus. And there is another sector which is m minus n over 4 pi. Is the A minus. This is similar to what people do in Latinger liquids when you do spin charge separation. Okay, it's a relative of that. And now the only thing is that the quasi-particle current couples in two different ways. You can similarly define an L plus and an L minus by a similar argument. And this has a 1 over root 2 L plus, A plus, and 1 over root 2 L minus A minus. Okay, so you see that it splits into two, but only one of them couples to the electromagnetic field. The other is neutral. Okay, so this is a charge sector, and this is the neutral sector. Okay. So this guy is charged. This is neutral. For the same reason, so you can think of this as a charge mode and the neutral mode, or the charge change Simons field. I can go to their respective edge theories. The edge. Now, I'm going to have a phi plus and a phi minus, which are essentially, I can repeat basically the argument I made before. And the edge theory now is a sum of two terms over 4 pi, as before, d naught phi plus, d1 phi minus some velocity, which I will call the charge velocity, is not universal. The 1 pi plus squared. So this is one part. And then I will have the other sector, m minus n over 4 pi. And there is a subtlety here now. D naught phi minus, D1 phi minus an index that will be plus or minus. Essentially, the index is going to be the sign of m minus n, sign something which I will call the neutral mode velocity, d1 phi minus squared. Again, it's a sum of two types of edge theories, except that they have two different velocities. That's non-universal, but there is a sign here. So if m is greater than n, they are co-moving. If m is less than n, they are counter-propagating. Because essentially these are both chiral, but if s changes sign, this will be anti-chiral. Okay, so this actually, so for instance, in the 2/3 case, you have, it's an example where you have states that do these things. So typically, due to effects that have to do with the Coulomb interaction, the charge mode is usually not only larger than the velocity of the neutral mode, but usually substantially larger by an order of magnitude, at least in numerics. Okay. Okay, so maybe I should stop now. So tomorrow we will start with the CFT construction of the wave functions, and then we'll go to the non-abelian case from there.
Okay, maybe a few questions before we break for tea. And let's try to get back on track by meeting back here at 11. Okay, so just maybe a few questions and then you can bug Eduardo in private. Ankur.
Yes. So when we do this construction of these neutral modes on the edge,
Yes.
the way that Ken Fisher original paper does it is they have to think about these disorders.
No, disorder is a separate problem. I like to stay away from the dirt if possible.
Sure, but when
disorder plays an important role when they are, particularly when they are counter-propagating. When they are co-moving, it does play a role. There is some renormalization, but because the edges are chiral, it's a minor effect. When they are counter-propagating, you have to be more careful.
Precisely. So what my question was about. So here, without actually going to this disorder business, I could already see that there is a loud description which is completely described in terms of neutral modes. So
there's always going to be a charge mode, remember?
There's always a charge mode. There's a charge mode, then there is a neutral mode.
Yes.
However, the way I was used to think is that it's the thermal conductance that you have to conserve, which allows you to break it in this language. But we haven't talked in this language how to think about thermal conductance, right?
No, I haven't, and we can do that later. Hopefully, we'll do that tomorrow. I keep adding more topics for tomorrow. Otherwise, it will be a very dense lecture. Okay. Okay. And your point is well taken. So the fact that there is a neutral mode, in fact, shows up into something else. So there is a different one. The reason we call it one the charge mode, the other neutral mode, is the charge mode is responsible for the transport of charge. So the neutral mode transports only energy, heat, in other words. So it shows up in the thermal conductivity, and the thermal conductivity does depend on the state. For instance, the two-thirds state has a peculiarity that, at least in the absence of disorder, the thermal conductivity is zero. Okay, they cancel each other out because they are counter-propagating. Okay, fine. I have seen. You don't want me to go on my. I agree with you because it's measured globally, not of course. We don't measure that locally. Yes, thank you. Yes, no. This is a relevant question for people coming from the Weizmann Institute. That's what they measure there. Okay, so they are sure. You're absolutely right.
Okay, all pedantry aside, maybe we have one last question.
So the question is, this looks like Eduardo here. Yeah, this looks like.
I don't know if you were online or here.
This looks like more of a change of a basis.
More of the what?
Change of a basis that you just took
change of
linear
basis.
combination.
Yes.
So change of basis, of course, doesn't change the phase. In a sense, when we look at the edge, disorder is put and then it undergoes a transition and leads to this phase which is neutral and charge. Here it looks like interpretation.
No, neutral and charge is already seen here. If you calculate, so I didn't talk about this. When you do the CFT, there is a quantity called the central extension or the central charge of the Virasoro algebra associated with the chiral Virasoro algebra in this case, and they cancel each other out already, even in this case, even without disorder.
I see. Okay, so this change of basis is more to make it apparent, but even if I do not make this change of basis, this is inbuilt into the whole thing.
Yes, it is.
So
if you actually look at an observable, depends what observable you look at. If you can actually couple two, so if you actually have a bilayer system, then you can actually contact them separately.
Right.
So in that case, in some sense, there are two, you have to think of two gauge electromagnetic fields, two gauge potentials, one that talks to one of them and not the other. In the case of spin, you cannot do that because the spin is neutral, doesn't know about the electromagnetic field. So it doesn't really matter for that. So it depends on the physical realization, I suppose.
But does it mean that the zero which you have, so when it is neutral, neutral will have, so on an average, the neutral will have no charge, but it will have charge fluctuations.
Well, that's always true, and I will agree. Okay. One carries the total charge in this language, and the other doesn't carry charge, carries energy only. By the way, in this case, in addition to the whole conductivity, you can also describe something called the mutual conductivity of one fluid relative to the other. And this is also measured in experiment. Okay.
Thank you.
Well taken.